In this section, we're going to build on all of the theory that we've now accrued to make the intermediate network in Keras that we had created even better so that we can classify MNIST digits even more accurately than before. So to do that, you can follow along by heading into the DeepNet in Keras notebook that I've put in the repository. We're going to recreate that notebook here, which you're also welcome to do, by copying the intermediate net, heading into there, and renaming it. So to say a deep net, we're going to change the title in the file here, and we can change our comment as well. We're going to be setting our seed the same way. We're going to have some more dependencies than before, some more models, some normalization that we didn't have before, but we'll worry about that in a sec. We're going to load data in the same way. We're going to pre-process in the same way. And we're going to build a new neural network architecture. So let's delete everything below. And we will refill that in from the bottom. So let's reset our kernel. So we're going to restart and clear all outputs so that we're starting fresh. We're going to run these cells by clicking Shift and Enter. So we've set our seed. So you guys get the same results as me. And then we're going to add to our dependencies here. So what are new kinds of layers we've been talking about? Dense we've always had, but we're going to start playing around with dropout layers as well. We are going to be using batch normalization, which we've now talked about. So we can pull that in from here. There we go. And we're also going to be using L1 and L2 regularization, so we can get those from here. I think those are all the imports we're going to need for now. So let's Shift and Enter to execute that cell. Of course, we're going to load our data. And we're going to pre-process our data the same as before. So converting our MNIST digits from 28 by 28 pixel images to 784 length arrays, changing our highest value from 255 to 1 so that all of our darknesses in the training set are from 0 to 1. And of course we have 10 digits, 10 classes, and we're going to convert those to one hot encoding. And then now we're here designing our neural network architecture. So what have we done so far here? We started off with a single hidden layer, which training for one epoch just had 10% accuracy, so chance accuracy. That after a couple hundred epochs of training got much better, got to 87% accuracy and was still learning. Later on in a separate notebook, our intermediate notebook, we switched from sigmoid to tanh neurons, and that increased our accuracy after one epoch, as well as after many epochs. We switched to ReLU neurons, which had a similar effect on training, but we stuck with those through the rest, and we're going to continue working with ReLU now still. We switched from a mean squared error cost function to cross entropy cost function, and that allowed our training to go much more quickly, and we had much higher validation accuracy after a few dozen epochs of training. And then we also added in a second layer so that we had two hidden layers with a dense or fully connected second hidden layer to complement the first one, both with 64 neurons. And finally, at the end of the intermediate network notebook, we increased our learning rate from 0.01 to 0.1, and that enabled us to reach 98% accuracy nearly by the 23rd epoch. So now let's go over the best practices that we covered earlier on in this lesson. The first change that we're going to make is we're going to talk about switching around our initialization. Now, we didn't talk about initialization before, but it just happened to be that Keras, the defaults are already pretty clever, and so the default in Keras was already to be using Glorot uniform initialization for our weights. So we were already in pretty good shape with our initializations without even knowing it. When we get into the nitty-gritty of TensorFlow later on, we'll see that we need to be more careful about this ourselves. But for now, I can show you how you would have changed it. So if you wanted to change, say, from the default Glorot normal to Glorot uniform, you can do that here by changing this parameter, just like that. So it's just this additional parameter within the model add method. We're not actually going to change the initializer here in Keras. We're just going to leave it with the default for now. The change that we are going to be making here is we are going to be adding regularization to our network. So we talked about a few different ways of doing that, of reducing overfitting. So we'll try this first method, L2 regularization, to start. There are a few different ways that we can apply L2 regularization. So we can apply it to just the weights. That's called kernel regularization. We can apply it to just the bias. That's bias regularization. Or we can apply it to all of this, the activity coming out of the neuron. So that'd be activity regularization. Most of the time, we don't need to worry about regularizing the bias, and so therefore we also don't need to worry about regularizing the activity. So we can just focus on regularizing the weight or the kernel. So we set that here in our code by adding this new parameter, kernel regularizer, and we set that to the L2 regularizer. Now there is a hyperparameter here, which is the amount of regularization that we want, and 0.01 is a decent starting point. So let's try that out. Our model summary looks the same, and then we need to compile our model like before. So we're going to configure model, and I'm going to do that. Model.compile. The loss that we want is, of course, categorical cross entropy, because we had such great results with that before. Our optimizer is still going to be stochastic gradient descent. And we have our learning rate parameter set to 0.1 now. We can use that faster speed. And our output metric is still going to be accuracy. Let's give that a shot. And then we're going to train our model. So we do that by calling the fit method. We still have the same inputs, the same training outputs. Our batch size is 128. Now you guys have heard about that with respect to stochastic gradient descent. We're going to set some large number of epochs to train here for, some verbosity so we get output to screen, and we're going to validate our results as always on the X test and the Y test. So let's try to fit this model. So after a single epoch, we're seeing results not too far off from what we had before without regularization. You'll notice that learning is happening a little bit more slowly, but you should also be noticing that the difference between the test accuracy and the validation accuracy has gotten smaller, particularly at later epochs. So overfitting definitionally involves having our testing accuracy continue to get higher while our validation accuracy stops getting higher or even goes down. And so here with regularization, we're seeing validation accuracies that stay high. And so we end up hitting 96% accuracy by the 19th epoch. And so that's the effect of regularization on our performance here. It's not getting this huge increases in our validation accuracy. In fact, it's not really increasing it at all. So what happens if we, instead of using the L2 regularization, we try using dropout? So to do that, we do it in a rather different way. So we can delete our extra kernel regularization parameter here. And to add dropout, we actually add that between layers. So we specify, for example, model add dropout, and we need to specify what proportion of the neurons we want to automatically drop out randomly between each epoch. So let's set that to half of the neurons. That's typically a good choice. And we're going to add dropout in between a couple of layers here. So now let's restart and run all of our cells again and see how our results have changed. All right, so when we do that, we see our dropout layers here in the model summary, but they're not adding any model parameters to fit. We're seeing a similar kind of effect to regularization where we're getting high validation accuracy even where training accuracy is kind of low, but it's even more dramatic here with the dropout. So we only had 66% accuracy in training. Now in training, we only had half of our hidden neurons every time now because we're dropping out half of them. For the validation set, the Keras is adding all of the neurons back in, so we validate our results with all of the neurons. There's no dropout during validation, and we simply have all of the weights when we do that. So that's all happening automatically in the background, but that's what's responsible for our high validation accuracy here when our training accuracy is so low. The results after a bunch of epochs are pretty similar to what we were seeing with L2 regularization. So we're seeing about 96% validation accuracy a couple of dozen epochs in. And it seems to cap out around there. So is it possible to use multiple types of regularization at the same time? For sure. So we can have dropout and L2 regularization at the same time. So our dropout is still in there. We can add our regularization of the kernel back in. So let's stop our code from running. We're going to add a regularization. We're going to choose our L2 regularization again with the 0.01 parameter. That 0.01 parameter is something that we'll learn how to tune later on. And let's restart and run all of our cells now with two kinds of overfitting prevention happening. So when we do that, model summary still looks the same. And broadly, we're going to see the same kind of results here with this network using both kinds of regularization. However, what I found when I ran this on many epochs is that my validation accuracy stayed down. So when we were using dropout on its own, or L2 regularization on its own, our validation accuracy after a few dozen epochs was hitting a ceiling around 96%. But when we're using both, the validation accuracy seems to cap lower, around 93, 94%. So it seems like we've made a mistake there by having both. And from my experience, it seems to me that dropout on its own is typically sufficient. So we're going to pull our L2 regularization back out of the network. We're going to stick just with dropout from here on to regularize. However, we are going to add in a new kind of layers, something new. So we talked about batch normalization at the end of the last theory section. So let's add that in. We know that it's a best practice. We want to avoid covariate shift between layers. So we're going to add batch normalization in. We're going to add it after the dense or fully connected layers, but before the dropout. Empirically, that seems in my experience to be the best way to arrange these. So let's restart our kernel and run all the cells. With this simple network with just 2 layers, I don't see a huge difference from the kind of top performance we were getting before. So we're capping out at about 97% validation accuracy. So batch normalization doesn't seem to be having a huge impact here. But this isn't a very deep network. The batch normalization might have a bigger impact if we had a deeper network with more opportunities for greater covariate shift. It doesn't seem to be expensive for us to leave it in, so we're just going to leave batch normalization there. Another one of the items that we talked about was gradient descent in our last theory section. So we talked about adjusting our learning rate a bit. We've done that. We have a pretty fast learning rate now. We talked about mini batch size. We're going to deal with that later on. But for now, let's add in some second order calculations. So let's start to take advantage of momentum. So we're going to switch from our stochastic gradient descent optimizer to Atom. And recall that one of the beautiful things about Atom is that it allows us to have our learning rate decrease over time. So at the beginning of learning, when we have our random weights, our random bias initializations, there's going to be a lot of opportunity for learning. And so Atom will allow us to take large step sizes in the beginning. However, as we learn and as our weights and our biases become more optimized, we will be able to slow down our learning, and Atom does that automatically. So that's a brilliant thing. It should enable us to converge more accurately on the minimum of the cost minimum across all of our parameters. After a single epoch, we're getting 92% validation accuracy, which is pretty good. It's on par with what we've been seeing. Interestingly, it seems to be breaching 96% accuracy faster than before. So prior to switching to Atom, when we were just on vanilla stochastic gradient descent, it took about 20 epochs to breach 96% accuracy. And it seems like we're getting to new heights here more quickly. I can tell you that if you run this long enough, you will reach 97.3% accuracy, which is the highest validation accuracy that we've seen yet. So that's great. We're narrowing in on how to optimize this MNIST classifying network. Finally, we want to actually have a deep network. So up to this point, we've only had 2 hidden layers, and few people would call that deep learning. There is no question, however, that as soon as you have 3 hidden layers, that is a deep neural network. So let's see what happens when we triple. So we're going to replicate having 64 fully connected neurons in our new hidden layer. We're going to apply batch normalization to that 3rd layer, and we're still going to have dropping out half of the neurons at random with each training step. We're going to restart and run all cells again. Let's see what happens here. So our model summary should show a larger network, which it does. So now we have more parameters than before. We have this 3rd layer. And so we've added 4,000, 4,300, 4,400 neurons into our network. And you can see that our time to compute each epoch has slowed a little bit. So it went from 2 to 3 seconds to more like 4 seconds on my machine. Now, do we end up getting better accuracy as a result of adding in that layer? Not really. In fact, prior to adding in that layer, we were comfortably above 97% accuracy after a few dozen epochs. However, here, after adding in that third layer, we can only just barely touch on 97%. So it's a small difference. Adding in that extra layer is also making our network learn more slowly. So I'd say that the net effect of adding in this third dense hidden layer was not great. I don't think that that was a great move. So what kinds of changes could we make? Well, we've hinted a little bit about convolutional neural networks. So we talked earlier about the kinds of machine vision applications that they're used in. We briefly mentioned the word convolutional earlier in this lesson when we talked about layer types. Now we're going to dive into what they really are, and we're going to leverage them because I think they might be just the ticket to get our MNIST digit classification even higher.